Hello there. It is truly good to share this quiet moment with you. Tonight, allow your world to dim just a little, letting the silence outside become the silence within. Imagine we are sitting together, not under a roof, but under the vast, deep velvet of the cosmos itself. Up there, above the clouds of our dreaming, things are in constant, slow motion. Planets orbit, stars pulse, and across immense stretches of time and distance, celestial bodies find their way to each other. Sometimes, this journey culminates in a spectacular, slow-motion event, a cosmic meeting of giants that changes the very shape of the neighborhood. We are going to turn our gaze towards these moments of magnificent, universe-sculpting contact tonight. It's a tender look at how even the most powerful impacts in space are simply ways the universe reorganizes its beautiful, ancient material. We'll explore how these grand, deep space events shape the galaxies we call home. If this gentle wandering through the night sky brings you a sense of calm or sparks a quiet wonder, please consider offering a soft like and a quiet subscribe. It ensures this space can find other sleepy souls who need a moment of scientific comfort. For now, relax and let your mind drift. There is no rush. We'll begin our quiet exploration together. The idea of celestial impacts has always held a strange fascination, hasn't it? Though uncommon, even in our own time, news occasionally surfaces about a cosmic pebble finding its way to Earth, and they make for such dramatic subjects in disaster movies. Why is this so? Perhaps it's because these powerful encounters once played a role in reshaping the very world beneath us. Think back to that moment 66 million years ago, when a grand collision may have caused the mass extinction that wiped out 76% of all species living on this planet. Was that a singular event, or is it something that could happen again? And if a large celestial body were ever on a collision course with Earth, could we really prevent it, protecting our shared home, using our current knowledge and technology? Major impact events have significantly etched their mark onto Earth's history, like a timeline drawn with cosmic scars. If we travel back to the very early solar system, one of the biggest impacts in our history might have actually formed our beloved moon. That was when a planet-sized object, which scientists call Theia, gently collided, yet immensely, powerfully, with the young Earth. As time progressed, even the vast, water-filled oceans we have today may be thanks to icy collisions with early asteroids. And since then, these cosmic stones have contributed to several mass extinctions. One of the most famous impact events left behind the Chicxulub crater, which is believed to have caused the dinosaurs to say their final goodbye 66 million years ago. You see, there is an inverse relationship between the size of an object and the frequency of these events. Small objects frequently find their way to Earth, while encounters with large objects are very rare. And as our solar system gently ages, large asteroid impacts become less common. When asteroids collide with something, they either fragment into smaller chunks or they become integrated into larger bodies, like planets. It is estimated that Earth gains about 15,000 tons per year this way from meteors entering its atmosphere. Impacts actually happen on Earth all the time, much more than you might imagine, but most are barely noticeable. Meteors, or shooting stars, are tiny objects with sizes ranging from sand grains to stones, only a few centimeters across. They harmlessly burn up as they enter Earth's warm atmosphere. How many of these tiny travelers do you think strike Earth's atmosphere on a daily basis? The figure may surprise you, around 25 million. And what do you suppose the largest meteor on any given day is likely to be? About 40 centimeters across? The largest one on a yearly basis is around 4 meters, and every century we get one that is at least 20 meters across. The objects that manage to survive Earth's atmosphere and land on the surface are called meteorites. These have to be somewhat larger than normal shooting stars to endure the journey, and most of the time, what's left of the object upon reaching Earth's surface is about the size of a brick. These objects cause large trails in the sky with spectacular colors, which we know as fireballs. Roughly every 2,000 years or so, a meteor about 100 meters across finds Earth, blasting through the atmosphere, causing significant damage to the area, both from the impact itself and from the associated airburst. And then you have objects large enough to truly threaten civilizations on Earth, objects over 10 kilometers that only come around once every several million years. The chances of anyone alive today encountering such an event are incredibly small, very close to zero. One comforting thought about these larger objects is that they are also much easier to spot. Scientists think they know of all nearby asteroids above the size of 10 kilometers with a very high degree of certainty. But smaller, less easy to spot meteors are still a significant threat on a more local scale. About 1,500 people were injured in 2013 when the Chelyabinsk meteor exploded over Chelyabinsk in Russia. Around 7,200 buildings across 6 cities were damaged by the explosion's shockwave. Luckily, no one was fatally injured during this incident, but imagine if such a disaster were to happen in a highly populated region. Needless to say, the results would be catastrophic. This is why it is so important for us to be able to detect and prevent this before it has a chance of happening. One of the ways we can do that is by finding and tracking objects in space that might be a future threat. And we are doing this faster and more efficiently than ever before. We've discovered over 20,000 new potentially dangerous asteroids in just the past 2 decades, with about 30 new discoveries added each week. Most of them, thankfully, have harmless orbits. But what would we actually do if we ever found an asteroid that was truly on a collision course with Earth? This was what NASA was attempting to find a solution for with its DART mission, or the Double Asteroid Redirection Test. DART was a shared project between NASA and the Johns Hopkins Applied Physics Laboratory, with international partners in Italy, Japan, and the European Space Agency. Its goal was to try and gently redirect an asteroid's path by purposefully colliding a spacecraft with it. Before DART came along, many different ideas were considered for the best way to prevent a cosmic collision. If we had enough warning, and if the asteroid was small enough, we could send a spacecraft to essentially ride along with an asteroid to act as a gravity tractor. Over time, the mere presence of the spacecraft could gravitationally influence the asteroid just enough to slightly redirect its orbit out of Earth's path. It sounds a little like science fiction, but in 2015, NASA published an article stating that this was actually a workable solution. Perhaps a more widely known idea is that of simply sending a nuclear device. Asteroids aren't very densely packed, so exploding them into tiny pieces ought to be easy enough to do. But although this idea was popularized by films like Armageddon, it might not work as well in practice, as the momentum of the asteroid would be largely maintained even as its form shattered into pieces. If the resultant pieces were big enough, this would have the unfortunate effect of turning a metaphorical bullet heading towards Earth into an equally deadly shotgun spray. A third idea involves sending reflective mirrors to an asteroid. It's a well-documented fact that as comets pass by the sun and heat up, they frequently start outgassing, giving them added propulsion away from the Sunday. Spacecraft with mirrors that traveled to an asteroid and reflected sunlight onto its surface at the right location could attempt to cause similar outgassing, letting the asteroid itself propel itself out of Earth's path with its own released gases. But the creators of DART settled on perhaps the simplest solution, and one that we had successfully pulled off before with a comet, to directly impact the asteroid. Not to blow it up, but to hit it just hard enough to gently knock it off course. The kinetic impactor plan was settled on. However, mission planners needed to select a suitable test asteroid to hit, and so scientists settled on Dimorphos. This asteroid was first discovered fairly recently, in 2003. It is the small moonlet in a binary system orbiting around the larger Didymos, which was spotted back in 1996. Dimorphos is only 160 meters across, which is much smaller than the 780-meter Didymos. It has an orbital period of 11.9 hours and maintains a distance of around 1 kilometer from its larger neighbor. The system orbits the Sun every 2.1 Earth years and made its closest approach to Earth in October 2022, coming within 10.6 million kilometers. This was the nearest it had been since 2003, making it the perfect time to visit it. It was this closeness that caused NASA to choose Dimorphos as their target. It was relatively easy to get to, but crucially, it was not so close as to be on a collision course with Earth. Scientists were confident that even once gently knocked off course, the Earth itself would not be in any danger. With their target set, NASA needed to build the perfect spacecraft to perform the deflection. Compared to other spacecraft, DART doesn't have a lot of complex frills. It's about the size of a refrigerator and weighs just 610 kilograms, which is minuscule compared to Dimorphos's estimated weight of 5 billion kilograms. DART has one single payload, an aperture camera called Draco, short for Didymos Reconnaissance, and Asteroid Camera for optical navigation, as well as sensors and an autonomous navigation system. It also came paired with a small secondary spacecraft called Lysiakube, making it a binary spacecraft, visiting a binary system built by the Italian Space Agency, ASI. Lysiakube is a small CubeSat with its own autonomous navigation system designed to separate from DART 15 days before impact. Lysiakube was tasked with recording the impact and its aftermath with 2 optical cameras named Luke and Leia. Yes, you heard that correctly, Star Wars fans. The Lysiakube weighs just 14 kilograms and is only about 30 centimeters long. It would fly by the asteroid system using its own autonomous navigation system. The DART spacecraft was also designed to be running completely autonomously due to the inherent latency or delay between sending and receiving instructions caused by the vast distances between Earth and the spacecraft. DART needed to locate the moonlet, detect a perfect spot for the impact to happen, and then aim itself appropriately. This is where DART's SmartNav came in handy. This autonomous optical navigation system could identify and gently distinguish between the 2 bodies, detect the target, and then quietly direct the spacecraft towards it. Imagine that the final act of this cosmic choreography took place in silence, unseen, unfolding in just the last hour before the dramatic touch. DART, launched so long ago on November 23, 2021, had spent 10 full months in a quiet, deep space slumber, simply traversing the distance. Then, the focus narrowed. 4 hours before the meeting, at a distance of 90,000 kilometers, DART's own internal navigation system gently awoke and took control of the spacecraft. 90 minutes later, the SmartNav system had made its final decision, locking the trajectory onto the target. There would be no turning back. When DART was 24,000 kilometers away, Dimorphos finally appeared on the camera, a faint light taking up just 1.4 pixels. It was one of the last frames from the Draco camera where both Dimorphos and its larger companion, Didymos, were visible together, a quiet family portrait before the event. As DART hurtled closer, covering the distance at 22,000 kilometers per hour, the tiny moonlet and its imminent point of contact came into sharper, more breathtaking focus. Look at this image, captured a mere 3 seconds before impact. You can truly see how Dimorphos is not a solid rock, but a delicate, loose pile of cosmic rubble, a whisper of matter essentially left over from the birth of our solar neighborhood. This remarkable photograph is the last fully transmitted image DART was able to send home. It was captured just 2 seconds before impact from a distance of 12 kilometers. To give you a sense of scale, each pixel represents about 3 centimeters of the moonlet's surface. And here, finally, is DART's very last, partially transmitted image. The connection to Earth was abruptly cut short by DART's predetermined final act. As strange as it is, this incomplete frame holds a special place. Its fractured nature seems to perfectly capture the drama and intensity, freezing forever the breathtaking instant. DART's 17.5 million kilometer journey reached its sudden, explosive conclusion. To the very last fraction of a second, DART performed its duty with incredible, quiet precision, a profound testament to the quiet brilliance of the minds that created it. We can see the entire sped-up sequence now, a time lapse covering the final 5.5 minutes of DART's trajectory. You might notice some of the images appearing slightly blurred. That was a sign of DART's ion thrusters activating in the final moments, causing gentle but noticeable vibrations in the spacecraft and its camera. This sequence is mesmerizing to me because of the sheer velocity to strike such a tiny, seemingly fragile object with such accuracy. It's astonishing that any of these pictures are in focus at all. Imagine how swiftly the camera had to adjust its focus, moment by moment, to the object rushing closer. I know you are holding your breath, wondering about the outcome. Did it work? Was the nudge successful? Let me gently confirm, yes, it was. And the earliest results didn't just meet expectations, they gracefully soared past them. The mission had set a humble benchmark for success, to alter Dimorphos's orbital period by at least 73 seconds, a small, hopeful change. Yet, the final data revealed a shift that was immense in its implication. DART shortened the orbit by a spectacular 32 full minutes. The moonlet's period was reduced from 11 hours and 55 minutes to 11 hours and 23 minutes. Even factoring in a 2-minute margin of error, this outcome was 25 times more effective than the target. A truly profound, gentle revolution in planetary defense. The energy released in that brief instant, was equivalent to 19 gigajoules, or roughly 5 tons of TNT. This concentrated burst of force carved a crater up to 150 meters wide into the surface of the moonlet. Considering Dimorphos was only 160 meters across to begin with, this was a significant, definitive mark. But the push was so strong, it didn't just leave a dent, it altered the celestial mechanics of the small body. Dimorphos's orbit around Didymos, which was initially almost perfectly circular, became slightly elongated, stretched out after the hit. The orbital time also continued to subtly settle over the following weeks, finally stabilizing at 11 hours, 22 minutes, and 3 seconds. And the shape of Dimorphos itself changed. Before the impact, it was described as an oblate spheroid, like a comfortable, slightly squashed sphere. Afterwards, the impact stress transformed it into a triaxial ellipsoid, perhaps best imagined as an oblong cosmic watermelon. It's captivating to contemplate the sheer forces required to subtly change the shape of an entire asteroid. This structural shift highlights the delicate rubble pile nature of asteroids like Dimorphos, bodies that are so loosely bound by gravity that a focused impact can rearrange their internal geography. But let us rest easy knowing this. Even with this successful, forceful collision, scientists are certain that the orbit of the main asteroid, Didymos, will not change enough to ever cross paths with Earth. The vital lesson here is that if we detect a true threat early enough, this simple, tiny push, a slight adjustment in cosmic velocity, is all we need to ensure the celestial body drifts harmlessly past our home. But why, mechanically, did the impact shorten the orbit instead of lengthening it? It's all thanks to the quiet mathematics of orbital mechanics. The crash delivered momentum that nudged Dimorphos ever so slightly closer to Didymos. And when an orbiting body gets closer to its gravitational partner, it must, by cosmic law, speed up its dance to maintain its path. Scientists verified this remarkable finding through patient observation from optical telescopes here on Earth, including the Southern Astrophysical Research Telescope in Chile. This facility happened to capture some of the most stunning evidence of the encounter, including a breathtaking photograph 2 days after impact, showing a 10,000-kilometer plume of debris trailing away, making the entire system look temporarily like a gentle, luminous comet. Because Didymos is a dual asteroid system, its combined brightness subtly fluctuates as Dimorphos passes in front of, and then behind, its larger partner. By patiently tracking this light curve, this gentle pulse of brightness, astronomers could precisely calculate the new, faster speed of Dimorphos's orbit. These findings were beautifully supported by complementary radar data collected by quiet observatories in California and West Virginia. DART and the ground-based telescopes weren't the only dedicated witnesses, though. The most personal, close-up images of the crash site were captured by the tiny secondary spacecraft, Lycia Cube, and they are truly spectacular. Lycia Cube had separated from DART 2 weeks earlier, continuing its own autonomous journey. 2 minutes and 45 seconds after the collision, Lycia Cube flew past the site, quietly photographing the impact zone, capturing the swirling plumes of ejecta as they blossomed into space. Here is a dramatic image of Dimorphos immediately after the event, with Didymos softly overexposed in the background. Notice the immense, graceful plumes of material radiating from the small moonlet. Some of them appeared to be spiraling, like the delicate tendrils of an astral vine. This swirling suggests the material's composition is varied, perhaps a mix of fine dust and coarser debris, which impact tests have shown can yield similar, beautiful ejection patterns. This next image is a slightly more distant view from Lycia Cube, with Dimorphos barely visible on the right side. The asteroid itself is almost entirely obscured by the huge, splashy cloud of material kicked up by the impact. Even our greatest cosmic sentinels, the Hubble and James Webb telescopes, quietly turned their gaze to document the aftermath. Hubble provided a spectacular series of images showing the subtle progression of the plumes, how they grew and multiplied over time. You might notice some of the plumes radiating outwards like gentle, luminous rays. Strangely, some of these rays appear curved, a small mystery of the cosmos that NASA is still trying to understand. While Hubble observed the event in the familiar, visible spectrum of light, the powerful James Webb telescope captured its own images in the infrared spectrum, the signature of heat. This was a challenging feat, given that Dimorphos was moving 3 times faster than Webb was originally intended to track. This final time-lapse starts right before the impact and extends 5 hours afterwards. Notice the sudden, brilliant flare of light that corresponds perfectly with the material violently released from the collision. I particularly love how the Webb images beautifully convey the spiraling motion of those plumes, that gentle, luminous swirl emanating from the asteroid's wound. In the quiet months and years to come, scientists will continue to sift through every piece of data from DART's impact. But the truly intimate, deep, investigative work will be carried out by the European Space Agency's follow-up mission, Hera. Hera is the patient observer, the essential next chapter. Launched on October 7th, 2024, it is scheduled to reach the Didymos system by 2026. It carries a sophisticated suite of instruments, cameras, a spectrometer, and an altimeter, all designed for meticulous documentation. Once it arrives, Hera will intricately document the precise size, shape, and composition of the crater DART left behind. But the most exciting promise is that Hera will conduct quiet observations of Dimorphos's internal and subsurface structures, peering beneath the rubble. This mission will deepen our understanding not only of the binary Didymos system, but will provide a nuanced, crucial insight into how a near-Earth object's physical characteristics, its fluffiness, its density influence the transfer of momentum, and exactly how kinetic energy transfers into an NEO and its ejected material. All of this combined will illuminate DART's success, providing a beautiful, quiet guideline for refining and improving deflection technologies for generations to come. When you couple this newfound knowledge with NASA's missions like NEO-Surveyor, which aims to find at least 90% of all 140-meter-sized asteroids or larger, it feels deeply comforting. It feels like humanity, for the first time, has actively and lovingly taken steps to reduce the chances of being struck by the kind of world-ending impact that once dictated the fate of the dinosaurs. The beautiful work of planetary defense doesn't end with a successful push. Even as we celebrate DART's precise hit, we must acknowledge the unseen threats, those quiet travelers moving through the dark. NASA maintains a continuous, watchful eye on most of the near-Earth objects we know about. Yet, some celestial visitors, like the elusive dark comets, are notoriously difficult to spot. They simply don't reflect much visible light back to us. That is where a future mission called NEO-Surveyor steps in. Proposed for launch in 2028, this silent sentinel will scan our solar neighborhood, not with visible light, but by taking infrared readings. It will detect those hard-to-see asteroids by sensing the gentle heat they radiate after being warmed by the distant sunday. More importantly, it will be able to spot those objects approaching us from our blind spots, those coming directly from the sun's direction, which ground-based telescopes often miss due to the overwhelming glare. With the ability to detect even the most secretive near-Earth objects, the technology proven by DART becomes a reliable shield, a quiet promise to keep our world safe. So there it rests for now, our first deep dive into the DART mission. We have truly just scratched the surface of what is possible in deflection technologies. But when you look at the sheer precision and unexpected success of this one mission, it feels as though the future of planetary defense has taken a brave, incredibly promising first step. It makes you wonder, doesn't it? Do you think this careful, focused mission was worth the effort? Do you believe this technology will ever need to be fully deployed in our lifetimes? The quiet wonder of the cosmos extends far beyond asteroids. If you have ever lifted your eyes to the night sky and seen a comet streaking by, you understand the profound sense of awe these icy visitors bring. Throughout human history, these bright-tailed objects have been seen with both wonder and fear, often considered harbingers of profound change. Yet, in the last 50 years, the script has quietly flipped. It shifted from them coming to visit us to us being able to reach out and visit them. Scientists had long pondered the fundamental nature and origin of comets. Where did they begin their journey? What ancient processes formed their icy hearts? In 1986, the first probe was gently launched to image Halley's Comet, and the patient search for answers truly began. But to truly unlock the secrets held within a comet, more than just distant photographs was needed. A more physical, tangible approach was necessary. Between 1999 and 2005, two separate, groundbreaking probes were launched. Their missions were designed to interact with comets in ways that were utterly unprecedented. One probe carried special collection equipment designed to quietly scoop up cosmic dust directly from the comet's icy tail. This would allow scientists to analyze the delicate chemical makeup of these frosty harbingers, seeking clues about the early universe. The second probe, however, took a far more forceful approach. Rather than gently collecting stardust, this second machine was designed to crash headfirst into the surface of a comet, detonating with the force equivalent to 5 tons of TNT. The goal was to study what could be learned from the resulting crater and the debris it spat out. And yet, although these two missions were intended for two different comets, fate, or perhaps cosmic chance, unexpectedly brought them both together at one particular celestial traveler, Comet Tempel 1. Join me now as we gently explore the explosive yet profoundly insightful story of Tempel 1 and how the Stardust and Deep Impact probes both played a crucial part in discovering what lay at the very heart of this ancient, space-borne nomad. In the quiet early 90s, comets remained largely an enigma. By 1999, 8 different spacecraft had been launched to investigate comets in our solar system, with 5 of those having flown closely past Halley's Comet in 1986. Beyond that, only 2 other comets had been visited, Comet Giacobini-Zinner in 1985 and Comet Griggs-Skellerup in 1992. While some beautiful, fascinating photos and small dust samples had been taken from as close as 200 kilometers, to the surfaces of these incredible celestial bodies. Their nebulous comas and tails comets still held many deep mysteries. What was their internal structure truly like? What were they made of at their core? And how, in the grand scheme of time, had they formed in the first place? In 1999, NASA scientists quietly proposed a daring plan, hoping to answer some of these persistent questions. It was proving difficult to understand the internal architecture of comets simply by looking at their fluffy surfaces. To truly know what was going on, scientists realized they needed to dig a little deeper, figuratively and literally. Their plan was elegant: to intentionally create a crater in a comet using a dedicated impactor spacecraft, which would collide with the comet at extremely high speeds. Since they would know the precise mass of the impactor and the speed it was traveling, they could calculate valuable information about the comet from the resulting crater's size. For example, they could determine whether its surface was a very loose aggregate of ice and dust, or if it possessed a surprisingly hard, frozen shell. The comet they chose to target was a short-period comet known as Tempel 1, which had a nucleus roughly 8 kilometers long and 5 kilometers wide. Scientists weren't exactly certain what would happen when the impactor struck. Perhaps the impactor would punch straight through like hitting a deep snowdrift and fail to create a true crater at all. There were many competing theories, and scientists were incredibly eager to find out which one the cosmos favored. NASA approved the ambitious project, giving it a budget of $330 million and christening it Deep Impact. You might instinctively think this was a deliberate reference to the 1998 Hollywood film of the same name, but seemingly, the names for both the scientific project and the film had been conceived independently around the same time. Quite a remarkable, gentle coincidence, if true, especially since the film Deep Impact was about scientists attempting to blow up a meteor on a collision course with Earth by flying a spacecraft carrying nuclear warheads into it. There certainly seemed to be some uncanny similarities to the NASA mission, especially given that NASA scientists actually worked as consultants on the film. I must confess, I don't entirely accept NASA's claim of pure coincidence. Fortunately for Earth, there were some crucial differences between the fictional film and the real mission. Tempel 1's orbit was nowhere near that of Earth, and given the impactor's small size compared to the massive comet, there was zero chance of knocking the comet off its current trajectory by more than a tiny fraction, perhaps a centimeter or so. It would be more akin to a small fly hitting the front windshield of a massive truck. Additionally, unlike the dramatic film scenario, nuclear devices would not be necessary to create a crater on Tempel 1, nor would any form of conventional explosive. The sheer speed and kinetic force the impactor would carry when it collided with the comet's surface would be more than enough to create the required crater, which some predictions suggested would be roughly 100 meters across and 30 meters deep. With the mission given the green light, scientists began the focused work on the Deep Impact spacecraft. The spacecraft was cleverly designed in two primary sections: the impactor payload and a larger flyby mothership to carry it and record the results of the final collision. The flyby section weighed 601 kilograms and was 3 meters long. It housed the main scientific instruments, solar panels, a debris shield, and two powerful cameras, the high-resolution imager and the medium-resolution imager. These cameras would take detailed photos of the comet after the impact, as well as assist in the crucial final stages of navigation. The impactor itself was smaller, only 372 kilograms, but it was also highly intelligent, housing a camera of its own. This camera, the impactor targeting sensor, would take photos of Temple 1 right up until the very moment of impact, streaming those images back to its flyby parent, which would then relay the precious data back to Earth. There was considerable public interest in this daring mission, which NASA gently encouraged in 2003 by inviting members of the public to submit their names to be recorded onto a CD that was placed directly onto the impactor. Roughly 625,000 names were collected in this manner, destined to be carried directly to Temple 1's surface. On top of that, NASA deliberately timed the impact to take place on July 4th, American Independence Day. While this might partially have been because it was just one day before Temple 1's perihelion, its closest approach to the Sun, which could produce clearer images, I suspect the more likely and fun reason for this particular date was simply that the American scientists enjoyed the idea of a large cosmic firework. Deep Impact quietly launched on the 12th of January, 2005, atop a Delta II rocket. But then, a small problem arose. Within a day of leaving Earth's orbit, Deep Impact's onboard computers switched itself into safe mode, a state it should only enter if a critical fault was detected. Something on board appeared to be gently overheating. This gave the scientists a momentary scare, but fortunately, the cause of the problem was quickly identified as a minor programming oversight. The acceptable heat tolerances had simply been set too low, causing Deep Impact to believe its thrusters were overheating when, in reality, they were operating perfectly fine. Engineers swiftly corrected the issue, and Deep Impact was able to properly begin its 6-month mission, traveling to its rendezvous point with Temple 1. In that time, it traveled 429 million kilometers. It only had to course correct twice on the long journey. This was actually quite impressive, as the original plan had factored in 3 course corrections. The first adjustment was so incredibly precise that the third correction was deemed entirely unnecessary. On the 25th of April, 2005, Deep Impact caught its very first distant glimpse of Comet Temple 1. Of course, NASA scientists couldn't manually guide Deep Impact during the final leg, as there was a several-minute signal lag between Earth and the spacecraft. Deep Impact and Temple 1 were now roughly 130 million kilometers away from Earth, more than twice the closest distance between Earth and Mars. Deep Impact's internal, smart programming would have to gently guide it in for the final, critical segment of the journey. On the 29th of June, the impactor successfully released from the flyby section and gracefully positioned itself into the comet's flight path, preparing to crash into it head-on. This trajectory was chosen for a few key reasons. First, the front side of the comet was illuminated by the sunlight, which would allow for better photographs to be taken. Second, flying head-on allowed a greater accumulated speed to be reached, resulting in the maximum kinetic force upon collision. And then, on the quiet evening of July 4th, 2005, precisely 1 second away from the predicted moment, the impactor struck. The result was a magnificent, brilliant spectacle. Scientists were thrilled by the pinpoint accuracy. Deep Impact's payload, traveling at a staggering 37,000 kilometers per hour, connected with a kinetic force of 19 billion joules. This produced the spectacular, instantaneous bright flash you see here, an energy release roughly equivalent to 5 tons of TNT. This light show was far brighter than anyone had anticipated. It illuminated the surface of Temple, 1 inch, a sudden, intense burst. However, with the success of the impact came an ironic, unexpected complication. The tremendous energy of the strike kicked up a colossal cloud of dust and material, which completely obscured the flyby spacecraft's primary view of the impact crater. This dust and gas continued to gently outgas from the comet for the next 13 days, peaking dramatically about 5 days in. This made it incredibly difficult to capture clear images of the result of their interstellar bullseye. Yet, this massive cloud wasn't entirely a problem. It offered fascinating insights into the internal pressures and volatile nature inside the comet itself. Over that period, an estimated 5 million kilograms of water and between 10 and 25 million kilograms of dust were ejected into space from Temple 1. Fortunately, scientists could rely on other eyes to capture the grandeur of the explosion itself. The collision was observed by numerous telescopes, both on and around Earth, including the mighty Hubble, the Swift satellite, and even many telescopes belonging to quiet, dedicated amateur astronomers. Still, the obscured view posed a serious challenge. While the outgassing plumes were fascinating to record, the primary purpose of the Deep Impact mission was to capture precise, high-resolution photographs of the crater left behind. Without clear images of that result, many of the fundamental questions about Temple, 1, its structure, its density, its composition, would remain frustratingly unanswered. It was like receiving a beautifully wrapped gift. Temple 1 had been opened, but we still couldn't quite see the precious contents inside. Another craft, another dedicated set of eyes, would be needed to complete Deep Impact's unfinished mission. And, as fate would have it, another capable craft was already launched and peacefully drifting through space, having successfully completed its own previous assignment. It was about to receive a quiet, brand new task. It is time now to talk about Stardust. Let's travel back a little further to the late 1990 seconds, when the science of comets was even more mysterious and fragmented. Although we had sent 6 probes to visit these enigmatic celestial bodies, not much was truly known about their ultimate origins. At the time, the prevailing theory held that comets were not native children of our solar system, but rather ancient, foreign visitors, older than the sun itself. It was believed they were formed from the loose, pre-solar grains of dust that orbited other, distant stars before drifting through the interstellar medium, eventually being caught by the sun's vast gravitational embrace. Scientists believed this theory could be beautifully confirmed by traveling to one of these comets and delicately picking up some of this loose dust, the so-called stardust, floating in the space around them. By examining the isotopic composition of these particles, they could determine if the material was fundamentally different from the dust given off by our own star. However, this was a challenging mission, as is so often the case in space travel. It came down to the quiet tyranny of speed and energy. Comets race through the inner solar system at tremendous speeds, reaching up to 160,000 kilometers per hour. While it was physically possible for a probe to match that speed and fly alongside a comet, doing so would require an enormous amount of heavy fuel, making the craft too expensive and heavy to launch in the first place. Initially, the Stardust mission had nothing to do with Temple 1. For its primary target, scientists selected a comet known as Wild 2, pronounced Wild 2. They calculated that stardust could manage to get alongside Wild 2 at a relatively low closing velocity. However, this low velocity was still a breathtaking 6.5 kilometers per second, or 23,400 kilometers per hour. As you can imagine, attempting to catch even tiny particles at that speed would be extremely challenging. While the particles themselves were too small to cause irreparable damage to the Stardust spacecraft, that high speed would do severe, irreparable damage to the particles themselves. When an object collides at 23,400 kilometers per hour, the chances of it keeping its original shape and structure are incredibly slim. Scientists would learn little about the original composition and structure of these ancient particles if they were simply smashed to pieces upon collection, not to mention the warping effect. All that kinetic energy, suddenly converted to heat, would have on the molecular bonds within the dust. So, what was their gentle solution? What mechanism could they devise for safely catching objects traveling at those tremendous speeds? They realized they needed a cosmic airbag, much like the one that softens the blow for you in a car crash. They needed something that would not halt the particle all at once, but would reduce its speed over a slightly longer distance, gently reducing the crushing force of deceleration. For this purpose, they found an incredible material that was essentially solidified air. They decided to use aerogel. Aerogel is a fascinating, ethereal substance discovered in 1931 by Samuel Kistler, who made a famous bet with a fellow scientist, Charles Learned, concerning the nature of jelly. As you probably know, jelly is made of two parts: a solid structure, like a sponge, and water. When you remove the water, the solid part of the jelly normally shrinks. Kistler's bet was to be the first person to successfully remove all the liquid from the jelly without allowing it to shrink. In short, to create a jelly that was entirely filled with air, an air jelly. Without detailing all the intricate processes, Kistler won his bet, and in doing so, invented the first aerogel. Aerogel is truly remarkable because it is usually over 99% air, yet possesses the structural strength to support weights far greater than its own. Nowadays, it is typically made from silica composites rather than flavored gelatin, but it can be created from a wide range of materials. It is incredibly light, is strangely an even better insulator than regular air, and most importantly for stardust, when particles hit it, it offered just the right amount of gentle resistance to slow the particle down without causing it to completely denature or destroy itself. The microscopic trails left behind in the aerogel would also be invaluable, allowing scientists to pinpoint exactly where a rare particle had been captured. Stardust was fitted with a large, tennis racket-sized aerogel collector tray composed of 90 separate blocks of aerogel, 3 centimeters thick, with over 1,000 square centimeters of surface area. This tray would be deployed from inside the main body of the spacecraft only when sampling was to take place. Stardust was also designed to capture samples from the interstellar medium itself, providing a baseline for comparison and helping us learn more about the everyday dust in our own solar system. Once the mission had collected these invaluable samples, it would store them on a special sample return capsule, SRC, which would be fired back towards Earth for re-entry and collection. This SRC was 80 centimeters by 50 centimeters, weighed 45 kilograms, and was fitted with an aero shield, navigation aids, and a parachute. Also on board Stardust was a navigation camera, a cometary and interstellar dust analyzer, and a dust flux monitoring system, among other scientific devices. The probe launched on the 7th of February, 1999, and spent the next 5 years journeying through space, even passing the asteroid 5,535. Anna Frank along the way, capturing some distant photos. But on the 2nd of January, 2004, it finally arrived at its primary target, Comet Wild 2, and what it found was immediately extraordinary. Scientists had entered the encounter with modest expectations for Wild 2. Some NASA scientists had even described their expectation that it would be a rather bland object, looking somewhat like a featureless black potato. However, this is absolutely not what they found. Instead, the surface of Wild 2 was surprisingly dynamic, covered with spiky pinnacles, hundreds of meters tall, sheer cliffs, and massive holes actively jetting dust and gas out into space, even on parts of the comet that were pointed away from the sun and were expected to be less reactive. In short, the surface of the comet was unexpectedly active and possibly self-renewing. Something else was just as notable for its absence: craters. Unlike almost every other body in our solar system, whose surface is exposed to space, there were almost no visible craters on the surface of Wild 2. This placed it in stark contrast to places like Mars or our own moon. Given the presumed age of Wild 2, it surely must have encountered other impacting objects. So, where had these ancient craters gone? This suggests that the comet's surface can either be active or self-renewing, gently erasing signs of visible impacts over short astronomical timescales. And, of course, during this critical flyby, Stardust had its aerogel collector exposed, and it was rapidly, gently collecting dust samples. Just listen to the frequency with which dust struck the spacecraft during its passage. The samples were carefully stowed away, and upon reaching the vicinity of Earth, Stardust quietly ejected the SRC. The angle of re-entry had to be flawless, as the capsule was traveling at tremendous speed. If the approach angle was too low, it would simply skim off the atmosphere and be lost back into space. If the angle was too high, the frictional heat would disintegrate the capsule and its precious cargo. It was with immense relief that the DC-8 NASA airplane monitoring the sky saw the capsule approaching at exactly the right second and the right angle. The SRC landed gently in the Utah desert, where it was recovered. Everything had worked and deployed just as it was designed to. And taking the samples back to the lab, scientists learned another completely unexpected, profound fact about Comet Wild 2. It was not a visitor to our solar system at all. Contrary to what had previously been believed, Comet Wild 2 had not originated from another star. It had been born from our own cosmic cloud. By comparing the isotopic composition of the particles Stardust collected with samples known to be from our own solar system, it was proven that Comet Wild 2 originated right here. And, contrary to what all the ice on its surface might lead you to believe, the rock at its center was formed under white-hot conditions. Structures called chondrules and calcium-aluminum inclusions were both found among the samples Stardust collected. These are structures that only form under incredibly hot conditions and can be found in other asteroids between Mars and Jupiter. So, scientists had to completely rethink their theory that comets formed solely in cold conditions at the far edge of the solar system, even if they do spend time there. It turns out that both fire and ice go into the making of a comet, and thanks to the careful, delicate way the particles had been collected, scientists were able to find one last surprising thing within the aerogel: the amino acid glycine. Amino acids are the vital building blocks that make up the proteins essential for all living things. Although this certainly doesn't mean anything was alive on Comet Wild 2, it does lend powerful weight to the idea that it was from comets such as this, crashing into our early Earth millions of years ago, that life's first essential building blocks found their way to our planet, a tantalizing glimpse into our own deep origins, which I'm sure you will agree is a profoundly comforting thought as you drift off to sleep. Given the incredible discoveries yielded by the Stardust mission, the ancient dust particles, the unexpected heat signatures, the fundamental building blocks of life, you might have assumed its work was complete. But NASA, in its quiet dedication to maximizing knowledge, is always hesitant to let a perfectly functional spacecraft drift into silence if it still holds potential. And Stardust still had precious fuel remaining in its tank. So, when the critical question arose in 2006 of how NASA could finally capture that essential close-up image of the crater on Temple 1, the answer came back as Stardust. It was a name put forward not just for convenience, but for an intriguing, unique opportunity. Calculations showed that Stardust had just enough fuel reserves to undertake a 6-year, winding journey through the solar system to reach Temple 1 again. This would mark a significant first, the first time a comet was visited and then revisited years later. This offered a rare, compelling chance to see how Temple 1 had evolved, how its surface had changed during the time it had completed its orbit around the Sun since the dramatic encounter. When Deep Impact made its first pass, it only managed to image about 1/3 of Temple 1's surface. But even that limited view was enough to identify mesmerizing geological features, layered terrains that hinted at its formation history, smooth flows that stood in sharp contrast to the rougher surrounding material, mysterious crater-like vents, and sheer cliff faces. Seeing how these features had changed after years orbiting the Sun would provide profound insight. Stardust would also be able to photograph areas previously unseen, giving us a far greater, richer coverage of the comet's geological story. There were clear, quiet advantages to repurposing Stardust. It was significantly more cost-effective to utilize an instrument already launched and performing flawlessly than to conceive, develop, and launch something entirely new. Stardust's original shielding was specifically designed with cometary exploration in mind, a feature that would prove invaluable later for reasons we will see. Crucially, it already possessed all the necessary camera equipment to take the precise images required. And so, the mission was approved and given a new name to match its new, extended assignment: the Stardust New Exploration of Temple 1 mission, or Stardust Next. Achieving this gentle reunion wouldn't be easy, of course. To conserve every drop of fuel, course corrections had to be calculated and executed years in advance. The challenge was compounded by the fact that Temple 1 doesn't simply glide static through space. It quietly spins once every 40 hours. Therefore, the challenge was twofold. It wasn't just a matter of figuring out how to get Stardust to meet up with Temple 1. NASA had to ensure that the meeting happened precisely when the cratered, impacted side was facing both the sun for illumination and facing stardust as it flew past. In effect, even though Temple 1 was too distant and too small to clearly resolve its surface features from Earth, the team had to calculate every single 40-hour spin Temple 1 would make for a full year ahead of the rendezvous to ensure the arrival time matched the perfect orientation. With Stardust's dwindling fuel reserves, there was almost zero room for error. Incredible precision and beautifully accurate models were required. To achieve this, NASA enlisted the quiet, patient help of dozens of observatories spanning the globe. Temple 1 was little more than a tiny, indistinguishable dot in the night sky from Earth, making it impossible to track its surface features. However, its slightly asymmetrical shape meant that its overall brightness subtly fluctuated as it traveled, dimming slightly as a narrower profile turned our way, then brightening as the wider profile rotated into view. These regular intervals of flickering light allowed a detailed rotation model to be created with a high degree of confidence. Scientists meticulously counted the comet's spins, hour by hour, year after year, knowing that missing a single rotation count could mean the complete failure of the primary mission objective. Their orbital model had to be flawless. Stardust spent years traversing the cosmos, engaging in one final Earth gravity assist, a gentle slingshot maneuver, and completing multiple laps around the sun before executing its final, critical adjustment a full year before its scheduled arrival at Temple 1. This subtle burn was designed to alter its arrival time by a small yet immensely significant 8 hours. Stardust was now locked onto its path. A year later, as it closed in on the comet, Stardust's protective shields began to detect sounds, the tiny, sharp clattering of minuscule particles. Temple 1, true to its cometary nature, was still gently ejecting dust and small rocks into space. Stardust was struck dozens of times. Although these projectiles were minuscule, perhaps a millimeter at most, some of these hits carried enough force to pierce the front shielding, cutting through a graphite cyanide honeycomb sheet as thick as your finger. Still, Stardust bravely survived the barrage, and on the quiet evening of February 14th, 2011, Stardust made its flyby. It passed at a distance of 181 kilometers and captured an essential 122 images. I find it rather endearing that scientists chose yet another holiday for a Temple 1 visit. They chose Independence Day for the initial impact, and here, for a less violent, more observational visit, they chose Valentine's Day. Scientists had to wait for patient hours for the images from Stardust to make the long journey back to Earth. But when they finally arrived, NASA saw that they had achieved another magnificent bullseye. They had correctly predicted the rotation of Temple 1 to an astonishing accuracy of a single degree. Right there on the comet's surface was the distinct, unmistakable crater left by Deep Impact's payload. The extended mission was a complete, quiet success. From the high-resolution images Stardust took, scientists were finally able to precisely calculate that the crater was approximately 150 meters across, making it 50% larger than they had originally predicted. From this crucial piece of data, they learned that the surface of Temple 1 was composed of an extremely fluffy material, made up of more dust and finer material than even a powdered snowbank. The surface was incredibly porous. In fact, they were able to estimate that 75% of the comet's entire volume was actually empty space. The whole structure was simply held loosely together by its own weak gravitational forces. From analysis of the material that had been ejected during the deep impact collision, scientists were able to identify several intriguing chemical components, including clays, silicates, sodium, and even complex organic material. While this is not life itself, these carbon-rich materials may have been carried to Earth by comets such as this millions of years ago, potentially providing the vital starting materials that allowed life to blossom here. Not only that, but the revisit allowed them to see profound changes that had taken place on Temple 1's surface in the intervening years. 3 distinct pits that had previously existed had merged to become one. A nearby cliff face had eroded back around 20 to 30 meters. This confirmed that Temple 1's surface is a dynamically changing place, constantly being reshaped by the sun's energy and its own volatile nature. This led to interesting new questions about how these formations were created and destroyed in the first place, a delightful puzzle for scientists to quietly ponder. So, Deep Impact's mission finally had the essential visual closure it needed, and Stardust's extended journey had been a resounding, peaceful success. But this was not the true end for Deep Impact either. Following quietly in Stardust's footsteps, Deep Impact's flyby spacecraft was later given a third mission, entitled EPOXY, short for Extrasolar Planet Observation and Deep Impact Extended Investigation, which in 2007 saw it heading off to investigate other comets and taking hundreds of thousands of photos before ultimately dropping out of contact in 2013. But by then, Deep Impact had already contributed significantly to advancing our profound understanding of comets and the earliest days of our solar system. What about Stardust? After its extended, successful mission, scientists noticed there was still a tiny bit of fuel left in its tank, so they decided to run one final experiment. Firing the thrusters for as long as it could, they checked to see if their mathematical models of how much fuel Stardust held matched the real-world performance. Right to its very last breath, Stardust kept gently doing science until the end. When at last all its fuel was finally used up, it sent one final transmission to Earth, acknowledging that it was being powered down for good. Now, it rests peacefully among the stars. Comets are truly fascinating things, and it was thanks to the incredible, dedicated work of the Stardust probe and the Deep Impact mission that we were able to learn a great deal about their inner composition and workings. While still retaining their ethereal beauty, we have gently pierced through their layers of enigma. We now understand that they are not some alien visitors, but originate right here from the very stuff of our own solar system. And they may have even carried the sparks that led to the blossoming of life itself on this planet. And all of this profound discovery was made possible by human ingenuity and quiet precision. So, the next time you happen to see a comet with its beautiful tail flaring out across space, it will no longer be quite so mysterious or foreboding. They may, in fact, be a deep, ancient reason that you are quietly resting here today. And all it took to uncover this truth was to delicately catch the dust from one and to gently punch another really, really hard. Our beautiful blue planet is accompanied by just one moon, a constant companion that appears so battered and solemnly scarred. It's clear that our gentle satellite has been struck countless times, smashed with such force that it left behind massive craters we can easily see just by looking up into the quiet night sky. But here is a mysterious thought. This may not have been a slow, gradual siege, or a patient bombardment by the cosmos upon the moon's surface. Instead, the evidence whispers of a blitzkrieg, a sudden, furious attack. The scars etched on the moon suggest that these massive impacts may have all happened within a very short period of time, cosmologically speaking. Imagine a sudden surge of falling meteorites, sweeping across the moon in an apocalyptic, chaotic rain. Scientists have named this theoretical period the Late Heavy Bombardment, LHB. While it remains a subject of thoughtful debate, if it truly happened, it would have been a devastating chapter in our history, yet one with profoundly surprising consequences. It may, in fact, be a key reason why we are all here, resting peacefully today. But if this furious rain truly occurred, what could have possibly caused it? And if the moon was so intensely scarred, how did our own Earth manage to survive and avoid the same destructive fate? Join me now as we drift back in time, 4 billion years into the past, to unravel a story of magnificent chaos swirling around our newly formed sun, as its planets were still settling into the familiar, predictable orbits we know now. When the brave Apollo astronauts returned home from the moon, the rocks they brought back told a surprising, quiet story. The crews had collected samples containing impact melt rocks that had been superheated into magma due to a tremendous meteorite strike, only to gradually cool back into solid form again. But while the Apollo teams had collected these reconstituted rocks from different areas and different craters across the near side of the moon, almost all of them were dated to a narrow window of time, around 4.1 to 3.8 billion years ago. Very few samples showed evidence of older impacts. The quiet implication was this: for some unknown reason, during this intense period of roughly 500 million years, there was an abnormal, terrifying spike in falling meteorites that violently crashed into our moon. This idea became known as the Late Heavy Bombardment. This theory is still met with controversy. Not everyone agrees that the evidence definitively proves it happened exactly that way. Such is the nature of scientific debate, built upon limited, distant evidence. We don't get the opportunity to visit the moon often to collect more samples, so it's challenging to tell if some other geological process might be obscuring the true picture. But if the Late Heavy Bombardment did happen, what could have possibly triggered it? To answer that, we must gently consider the conditions back at the very dawn of our solar system. It is a well-known idea that our solar system was formed from an accreting disk of interstellar dust and matter 4.6 billion years ago, all swirling around a gravitational center that would eventually house our Sunday gravitational disturbances, cause some of this dust to gently bunch together. Once that happened, each larger ball of matter found itself snowballing in size. Larger clumps possessed a stronger gravitational pull, which, in turn, pulled in more mass, allowing the clumps to grow even larger. At this dramatic point in history, the vast spinning disk of matter from which our entire solar system was created had clumped together into planetesimals. These small, rocky bodies were further attracted to each other, violently crashing together to form the true planets we know today. Within a mere 100 million years, this process of planetary accretion had effectively swept up almost all the material closer to the Sun to form what we call the terrestrial planets: Mercury, Venus, Earth, and Mars. One of these monumental final impacts formed our moon, flinging a massive lump of molten rock into space, which cooled into a sphere and has remained in orbit around our planet ever since. There would still be some isolated leftovers between these nascent planets. Some are still out there today, like the 1.5 million floating asteroids quietly orbiting the Sun between Mars and Jupiter. But this initial violent process had largely cleared out everything in the inner solar system. Under this straightforward model, you would expect to see more impacts at the very beginning of the solar system, but fewer and fewer impacts as time went on, not a sudden, frightening spike 4.1 billion years ago. So, why could there have been a colossal surge in impacts during that period, one that gave our moon such a brutal beating? This has created quite a puzzle for scientists, although some now believe they may have found the gentle yet powerful solution. The finger of suspicion points towards Jupiter, the magnificent giant of our solar system, possessing more than 2.5 times the mass of all the other planets combined. Jupiter was the first planet to fully form, along with Saturn, as our solar system began to take its final shape. The hypothesized behavior of Jupiter is key to explaining the observations that led to the proposal of the late heavy bombardment theory. Jupiter is not thought to have always quietly orbited at its present distance of 768 million kilometers from the Sunday. Initially, Jupiter actually moved inward toward the Sun, reaching roughly where Mars orbits now, since Mars and the other inner planets didn't fully exist there at that point. It then abruptly changed direction and began to pull away again. All of this chaos possibly happened within just a few million years. What made Jupiter behave like this? The short answer lies in its delicate yet powerful relationship with Saturn. When Jupiter first formed, there was still a huge amount of gas swirling around our developing Sunday. This gas acted like a subtle brake, dragging Jupiter inward towards the center of the newly forming solar system. Once Saturn had formed, it also began this inward journey toward the Sunday. However, the two new gas giants became gravitationally bonded as their massive gravities combined. The sudden, strong tug of Saturn, pulling from behind, was enough to arrest Jupiter's grand destructive procession towards the solar system's inner territory and gently pull it back out to the stable orbit we see it at today. But this planetary procession was not without impact. Quite literally, our current asteroid belt, with its 1 to 2 million known asteroids, potentially represents less than 1% of the matter that used to reside there. So, when Jupiter came sweeping through, its massive, far-reaching gravitational pull violently disrupted a vast number of orbits. Many of those displaced objects suddenly began to fall inward, heading for the inner solar system. Two distinct types of asteroids were drawn into this catastrophic process from both the inner and outer solar system. This detail becomes quite important later. Not all asteroids are the same. You may be familiar with the terms S-type and C-type asteroids. S-type asteroids are the stony asteroids from the inner solar system. They are mainly made up of silicate materials and nickel iron. They are generally drier because they formed closer to the intense heat of the Sunday. C-type asteroids, or the carbonaceous chondrite asteroids, are the most common and are among the most ancient objects in our entire solar system. They come from the outer asteroid belts, and they contain much larger amounts of something that would later prove absolutely crucial to our planet: water. And all of these displaced asteroids, a massive, mixed hailstorm, began to fall through the patch of space our planet was quietly orbiting. So, to answer the initial, compelling question, how did the Earth avoid all these asteroids when the Moon was constantly and apocalyptically bombarded? The simple comforting truth is, it didn't. The timing of this chaotic event, as far as our planet is concerned, was crucial. By this time, 4 billion years ago, the surface of the Earth had cooled enough to form a more stable crust, what we know as the lithosphere today. This newly formed crust insulated everything above it from the enormous, searing heat of the magma below. The magma near the surface was still much hotter than it is today, around 1,600 Celsius, and it was much more liquid. Heavier elements, especially iron, had long since sunk toward the central core, leaving the lighter elements and minerals near the surface. As the asteroids rained down onto this newly stable surface, they brought with them a whole range of new elements and minerals that would remain as part of this surface layer. It is now believed that many of the important deposits we rely on today, ores and metals such as lead, nickel, copper, and gold, were delivered to Earth in this cosmic manner. More important than these valuable metals, however, was the arrival of water. Vast, almost unimaginable amounts of water, primarily carried by those C-type asteroids. Had all this water arrived earlier, when the surface of our planet was still hotter and less able to maintain a proper atmosphere, much or all of this water would have escaped back into space, potentially leaving the planet an arid desert, much like Mars and the Moon. Instead, surrounding Earth during the chaotic bombardment 4 billion years ago was a toxic atmosphere of methane and ammonia, covering an unstable but slowly solidifying surface of basalt-type rock. The rock was dark gray, almost black, with brightly glowing lava violently erupting through faults where the crust was shattered by the incoming asteroid hailstorm. Simultaneously, vast, steaming oceans of water were forming, helping to further cool the developing surface, a true, violent vision of fire and brimstone giving way to life. It is partly because of this churning, dynamic nature of the Earth's surface floating on liquid magma that today we see no trace of the ancient craters left by these impacts. The forming lithosphere was fractured into many small tectonic plates that moved around and recycled themselves much faster than they do today. Due to this constant geological churning, almost no trace of these early rocks or the initial impacts remains visible on the surface. The oldest surviving rock formations on our planet gently mark the end of the Hadean period, a time of immense heat and profound volatility. By this era's conclusion, the intense, apocalyptic bombardment of our world had likely come to a halt. The end of the Hadean also signifies the quiet beginning of a new crucial development in our planet's fascinating history: the very story of life. The origins of life's evolution on Earth have long been a subject of warm, persistent debate. What specific conditions could have led to the creation of that primordial molecular soup, rich with the key building blocks like hydrocarbons and other complex organic molecules? Interestingly, while the late heavy bombardment, LHB, remains a subject of controversy, this theory beautifully helps to provide a potential answer to this vital question. We now know that all 5 of the essential building blocks of our DNA and RNA actually exist, floating in space, and traces of them have been found on certain meteorites. While the small, fragile meteorites we see today burning up in the night sky could never deliver anything so delicate as these complex molecules to our planet's surface, they would incinerate long before reaching the stratosphere. The dynamics of the LHB were very different. When those much larger objects were raining vast amounts of water and ice onto our newly forming surface, it is certainly plausible that they gently seeded the earth with some of the crucial ingredients that made life viable. There is compelling evidence suggesting that life began to take root right at the moment this intense bombardment was finally ending, just as the new, warm oceans were forming. Finding definitive answers to many of these deep questions is almost impossible here on Earth because so little physical evidence remains from that chaotic time. This is why scientists are so eager to study the clues that may still be perfectly preserved on the Moon. The reason this evidence is so beautifully preserved on the Moon is that, unlike Earth, its surface was already quite stable early on, without the churning, recycling process of plate tectonics and erosion that occurred here. Thus, those ancient, massive craters remain intact, like pages preserved in a cosmic book. Furthermore, the Moon's surface is not constantly being eroded by weathering. There are no seas to grind down the rock, no wind, no acid rain to wear away the ancient surface. The dust that blankets the surface is simply pulverized rock, lying virtually undisturbed following those dramatic impacts from billions of years ago. We do have impact craters on our planet's surface, such as the famous Barringer crater in Arizona, USA, but that only dates back 50,000 years, a blink in time. Of the original craters from the late heavy bombardment era itself, there is absolutely nothing visible on Earth today. If such ancient craters do survive somewhere on our planet, they are likely buried deeply under later sediments or lava flows, and we may never find them. We have managed to make significant progress in understanding this early era, thanks to the astonishing 382 kilograms of moon rock brought back to Earth by the Apollo missions. Radiometric dating of these precious rock samples indicated that they were last molten during a narrow period, clustered around 3.9 billion years ago, a finding perfectly consistent with the theory that Earth and the other inner planets were being heavily bombarded by asteroids during that concentrated time. Those immense, dark, smooth areas you see on the Moon are where asteroids have impacted the surface with such force that rock melted into lava, which then flowed out and cooled, forming those characteristic smooth, dark plains we can see on clear nights. However, not everyone in the scientific community agrees entirely. As more refined analytic techniques have been developed over time, questions have been raised about the timescale and true duration of this period of asteroid activity. Some dating inconsistencies suggest that the craters may have formed over a much longer period of time, gradually tailing off from the initial planetary accretion that formed the terrestrial planets, rather than a single, sudden, concentrated period of activity. The material scientists have available from the Apollo missions is still limited, as the samples stem from just a few carefully selected locations on the near side of the Moon. Hopefully, more samples from future missions will resolve some of these quiet controversies. The NASA Artemis missions could see another landing on the surface of the Moon as early as 2026. I look forward to seeing what new, profound discoveries this might bring to light. The late heavy bombardment theory may not be a perfect, final explanation, but it tells a convincing, dramatic story that beautifully fits our observations of the Moon and the oldest parts of our planet's surface that we have managed to explore so far. Crucially, it provides some compelling possible answers to the vital question of how such a vast amount of water came to exist on the surface of what had once been a molten ball of rock. Whether or not this turns out to be the ultimate, correct story, the next time you gently fill your kettle or paddle in the sea, You might pause to remember where that water potentially came from, and how incredibly lucky the timing of it all must have been for that water to actually stay here and create a planet so perfectly conducive to the blossoming of life. I truly hope you will join me for the next video in this series, when we will continue to explore another chapter of the incredible ancient history of our beautiful blue marble planet Earth. The moon may seem like a barren, silent world, but if you take a closer, more patient look at its surface, you will find countless intriguing puzzles about its deep past, just waiting to be solved. The LRO, or the Lunar Reconnaissance Orbiter, has been diligently scanning the moon's surface since 2009, capturing super high-resolution shots from various angles. This gives us a view of the entire moon like never before. After looking at the mountains in the last installment, today we will look at some of the most interesting craters found on its face. Through the many surveying missions to the moon over the years, the entire satellite has been meticulously mapped out. You can actually view all the resulting data in a program called QuickMap, which is an accessible way to explore this quiet neighbor for yourself. Zooming out as far as we can go, on the far side of the moon, we find one of the biggest impact craters known in the entire solar system, the South Pole Aitken Basin, spanning an astonishing 2,500 kilometers across. Interestingly, this is where the Chinese Chang'e 4 mission successfully landed its rover in January 2019. The LRO was even able to gently image the rover from space. However, without the rover or any familiar size guide, you might immediately find something unusual about the lunar surface images: the complete inability to properly judge distances and scales. This is due to the lack of an atmosphere, the haze of which helps us gauge distance here on Earth, and the absence of familiar objects like trees or buildings, which help us judge scale. I will always try to include visual cues to help you appreciate the size of what you are seeing. As you can clearly see, the moon's surface is completely littered with craters. It doesn't matter where you are on the moon, there will be craters of various sizes. This immediately implies that the surface is incredibly old and has not been renewed by lava eruptions from the mantle anytime recently. The most recent significant eruption is thought to have happened over 1.2 billion years ago. It is estimated there are at least 300,000 impact craters over 1 kilometer across on the moon's side facing us, and millions more smaller than that. The moon can retain such small, faint craters because it has virtually no atmosphere. This means nearly every meteorite heading for the moon will strike its surface. Imagine how many shooting stars you see each night. Were it not for Earth's thick atmosphere, every one of them would impact our surface too. What is so interesting about each crater you see here is that you can roughly estimate how old it is by how eroded it appears. Craters that look very smooth, dark, and soft are much older than craters with lighter substances surrounding them, possessing sharp, defined edges. The bright patches haven't had as long for the unique lunar weathering effect to occur. But weathering on the moon? How can that be without wind or rain? This weathering is not caused by water or air, but rather by the constant, gentle stream of tiny micrometeorite impacts and the intense radiation pouring from the sun, which subtly dulls the thin outer layer of the moon's soil. If we look closely at the end of this image, we can see a relatively fresh crater, only a few hundred meters across. Using LRO's narrow-angle camera, we can get a close-up view of the spectacular effects of such an impact on the lunar surface. These linear patterns are the effects of the ejecta, the material thrown out by the collision. Finer dust would have been blown across the surface with significant force, while larger boulders didn't quite make it as far, instead leaving clear trails where they rolled away from the point of impact. The crater itself isn't super clear in this image due to the time of the lunar day this was captured. The sun is close to the horizon, casting long, dramatic shadows across the surface, though you can still see fresh, exposed material along the crater wall. Now, let's compare this to an old crater. Here, you can see a much smoother and darker looking crater, although it is still slightly brighter than the heavily weathered surface in the surrounding area. What I particularly love about this image, however, is that if we zoom in closely, you can see some ejecta that landed from another impact off the edge of the photograph. Here is a massive boulder that landed directly on the crater wall and then rolled halfway down, leaving a clear path. The only difficulty with these top-down perspectives is that they don't give you a true concept of depth. How shallow or how deep can these craters really get? Luckily, the LRO doesn't just scan the surface. It can also take more oblique angled shots of the moon, which beautifully help us appreciate the vertical scale and depth. Look at this fantastic image. The crater is around 21 kilometers across and contains some fascinating details all around its edge. Again, we can clearly see the trails left by huge boulders rolling down the steep slopes and very bright inner walls, which strongly implies it is a young crater. Yet, the material at the base is much darker. The contrasts are quite vivid, and it almost looks like some parts could have been liquid at some point. This is the truth. The impact would have initially melted the rock into lava, which then flowed to the bottom, collecting in pools that have since solidified. The impactor was likely 2 kilometers in diameter and hit the moon 10 times faster than the speed of a bullet. That would have been a catastrophic, yet beautiful, collision indeed. Another great image I must share with you is this one. This crater is 10 kilometers across. What is truly special about this one is its interestingly raised rim. This is another example of rock melting from the impact, but in this case, the molten rock slopped beyond the rim, flowing down the outer slopes before finally solidifying again. If we look closely around the edges of that immense crater, you can also see ejecta scattered across the surface, gently disturbing the ground and leaving brighter patches exposed. See, once you know what to look for, even our quiet moon suddenly becomes a place of profound interest. But those have been relatively pristine, single craters. What happens if a meteorite lands somewhere a little less conventional? Here is a beautiful example, a crater within a crater. The impactor struck the wall of the larger, older crater, which gave the resulting shape a slightly unusual, almost lopsided profile, although from a straight, top-down perspective, it still manages to appear quite circular. As a side note, this particular image is a true color image of the moon. Most images of the moon are captured in black and white to save bandwidth. Astronomers often prioritize sharp resolution over color. However, the lowest resolution camera on the LRO is capable of capturing color, and this is a beautiful example of that capability. But certain craters harbor secrets that are unconventional in other ways, too. There's a little understood phenomenon that scientists have struggled to explain so far: mysterious cool patches found on the moon after the sun goes down. We've mostly focused on the cameras aboard the LRO, but it carries a host of other specialized instruments, including the Diviner Lunar Radiometer experiment, which has meticulously mapped the moon's surface temperatures. The data revealed that there are about 2,000 specific spots on the moon that cool down significantly more than the surrounding areas once the sun sets. When the sun rises again on those spots, they quickly normalize their temperature and blend back into the background. The only things these spots seem to have in common are that they are always found around young craters, no smaller than 15 meters and no bigger than 2.3 kilometers. But the cool spots themselves are often much larger than the craters they encircle. Here is a heat map of the crater I just showed you. White represents the hottest parts of the image, and blue represents the coolest. As you can clearly see, a large cool region gently surrounds the young crater. There is an ongoing, quiet investigation to find the cause. What do you think could be the secret behind this lunar cooling effect? There truly were so many more beautiful images I could have shared with you today, but I will have to save them for next time. I just wanted to leave you with one final image that I found truly breathtaking. This crater, found near the south pole of the moon, is almost always shrouded in shadow. The sun never rises high above the horizon in this region, meaning only the peaks of the crater walls stick out enough to be briefly enveloped in light. What you are left with is a stunning contrast, almost like a celestial representation of the yin and yang symbol. This view has certainly become my new desktop background image. But this region isn't just an eerily beautiful place. It is actually one of the prime candidates for future human missions to the moon. The lunar South Pole is of particular, crucial importance because it is thought to contain millions of tons of water ice found at the bottom of craters like this, perpetually protected from the sun's rays. If there is ever to be a permanent future colony on the moon, this is precisely where it would need to be located. So there you have it, a quiet sample of some of the most intriguing craters on our neighboring world. If I were a superstitious person, I might advise caution when naming your space missions. When Russia named its first mission to the moon in 47 years, it was originally given the designation Luna Glob, which translates in English to lunar sphere. However, this name troubled Lev Zeleny, the scientific director of the Space Research Institute of the Russian Academy of Sciences. He felt that glob was too similar to a different, ill-omened Russian word, grob, meaning coffin. Zeleny changed the mission's name to Luna 25, intending to evoke the spirit of the earlier, successful Soviet Luna missions, which were the last time Russian spacecraft successfully landed on the moon. But perhaps it was already too late, and something of that original, darker name lingered, because we now know that Luna Coffin was a far more apt name for the ill-fated Luna 25. For the country that once fearlessly led the world in the space race, what exactly went wrong? Although we often focus on the missions of NASA or ESA here, Russia's space program, historically, has been a quiet powerhouse. Back when Russia was part of the USSR, it was the Soviet Union's launching of Sputnik 1, the first artificial satellite, that triggered the entire space race in 1957. And for a time, the Soviet space program seemed to go from strength to strength, achieving many firsts. It was the Soviet Union that put the first man into space, the first woman, the first multi-person crew, and even the first dog. Their rockets were the first to escape the Earth-Moon system, the first to impact the moon, the first to orbit the moon, and the first to take photos of the far side. Soviet cosmonauts performed the first spacewalk, and the USSR launched the first space station. To the eyes of many, and certainly to the pleasure of the Soviet leadership, the USSR appeared to be winning the space race. But beneath the glorious surface, not everything was flowing as smoothly as it seemed. The Soviet Union also tragically saw the first death during a space mission when the re-entry capsule's parachute of cosmonaut Vladimir Komarov failed to open upon his return to Earth. The only 3 men to have died in space were a crew of Soviet cosmonauts visiting that first-ever space station. Soviet launches were, in reality, plagued with frequent failures, but eager to maintain a flawless appearance in the eyes of the world, especially compared to their great rival, the US. The USSR simply didn't report any of its failed lunar missions. They pretended any rocket that didn't make it out of the atmosphere was never intended to be a moon mission at all. In truth, only about 34% of Soviet moon missions ended in success, a significant contrast to America's 60% success rate on equivalent missions. America landed the first man on the moon in 1969, and after that crowning, dramatic achievement, both global superpowers seemed to quietly lose interest in continuing the intense race, refocusing their space programs towards non-lunar pursuits by the mid-1970 seconds. Soviet cosmonauts never set foot on the moon itself. The USSR canceled all of its plans to do so, as the entire endeavor was ultimately seen as too expensive. Perhaps more importantly, what was the real point of going if you were only guaranteed to get there second? But with the turn of the millennium, and since the fall of the Soviet Union in 1991, the world's quiet interest in returning to the moon has been powerfully rekindled. Scientists realized that the moon would make an ideal stepping stone for human space missions heading to Mars. Its abundant resources, such as the newly discovered water ice, perfect for rocket fuel, air, and drinking water, and its low gravity, began to attract the attention of businesses for economic reasons. Nations began to seriously consider establishing permanent bases on its surface as a way of both advancing science and turning a profit. And of course, there is still a vast amount of quiet science to be done there, attracting those who wish to learn more about the formation processes of the moon and the cycles that govern it. Russia's old rival, the USA, began to quietly dust off their space programs. America started its Constellation program in 2005, clearly declaring their aim to go back to the moon. But now, other nations were also seriously joining the effort. India, which had not been part of the first race for the moon, began its Chandrayaan program for lunar exploration in 2000. Governments across the world believed that the potential benefits of going to the moon in this second rush were so great that nations who didn't go would inevitably fall behind. In the famous words of the Indian Space Research Organization, ISRO chairman Krishna Swamy Kasturirangan, it was not whether we can afford it, but whether we can afford to ignore it. Russia absolutely did not intend to be left behind. It was eager to pick up the grand Soviet legacy of space exploration. In fact, it beat its immediate competitors to the conceptual punch. Russia had already begun thinking about a new lunar mission as early as the mid-1990 seconds, when scientists Mikhail Marov and Eric Galimov put forward their detailed proposals to Roscosmos, Russia's newly restructured space agency. Their initial Luna Glob mission was approved and was originally intended to have a lot more components to it, including a penetrator for seismic sounding, a lander, and an orbiter. However, the project initially lacked enough political will and sustained backing. It faced severe budget cuts after the Russian financial crisis of 1998, when the ruble dramatically lost over 2/3 of its value in just 3 weeks. The mission was further marred in delays that repeatedly knocked it back and put it on hold. The penetrator and the orbiter were eventually scrapped, leaving just the lander as the reimagined plan for the mission, making it more economical. Russia desperately wanted to be a nationally recognized player in the space game, but didn't want to spend massive amounts of its budget on the plan. In 2005, Russia only invested 20 billion rubles, about $700 million in its space industry, compared to the USA's $15.6 billion. One strategic way to work around this low budget was to collaborate with other nations. Russia initially tried to work with India on the Chandrayaan-2 mission in 2007. The plan was that Russia's lander, Luna 25, would fly with India's orbiter and be the mission's crucial lander component. However, this low spending ultimately punished them, and Russian scientists were unable to get the lander's technology fully working in time for the initial 2013 launch date. India eventually decided to abandon the challenging collaboration and moved forward to complete Chandrayaan-2 on their own. Russia was left with the immense task of getting Luna 25 to the lunar surface solo. While India's Chandrayaan-2 lander tragically crashed into the moon, India was determined to try again with Chandrayaan-3. This set the former collaborators, Russia and India, on a new, quiet course. They became fierce competitors. Both nations had a shared, vital interest in the moon's south pole, where Chandrayaan-2 and other missions had previously confirmed the presence of water ice through spectroscopic analysis. Luna 25 and Chandrayaan-3 were now locked in a direct race to be the very first lander to successfully touch down near the South Pole and potentially confirm and sample that invaluable water ice. However, Russia soon faced a massive new problem: the invasion of Ukraine in 2022. Western countries were outraged by Russia's decision to attack its neighbor and quickly came together to impose massive, painful sanctions. This wasn't just economically painful. A vital element of these sanctions was a comprehensive ban on the trade of high-end computer chips and precision components. While intended to prevent Russia from developing high-precision ballistic rockets for military use, the ban severely impacted Russia's goals for its Luna program as well. European scientists and agencies began ending their decades-long collaborations with Roscosmos. In an interconnected world where Russia traded for much of its high-end components, Russia would now have to attempt this complicated lunar journey entirely alone. India completed Chandrayaan-3 and successfully launched it on July 14, 2023. The route they wisely chose to the moon was fuel-efficient but time-consuming, requiring over a month to actually arrive at the lunar surface. India estimated a final touchdown date of August 23rd. If Russia hurried and managed to complete its lander in time, it could still potentially arrive before India by taking a shorter, more fuel-intensive route, using Russia's powerful Soyuz 2-1B rocket. The Luna 25 mission had already been delayed multiple times, from 2021 to 2022, and then to 2023. In a bad stroke of timing for Russia, its crucial BIB navigation sensor failed to pass quality tests. This sensor relied on a specialized computer chip normally supplied from the West, a chip that Russia could no longer legally purchase due to the sanctions. Consequently, Russian scientists were forced to develop a new one on their own, the Bias-L. Luna 25 was finally cleared as ready to launch on August 11, 2023. It carried 8 unique Russian scientific instruments on board, including laser mass spectrometers, infrared spectrometers, cameras for imaging the lunar surface, and even a device for measuring dust and micrometeors. Luna 25 was designed to operate on the moon's surface for a whole year, enduring the freezing cold of lunar nights and the intense solar radiation of lunar days. It had the genuine potential to achieve excellent science. The Soyuz rocket proved powerful enough that it would get Luna 25 to the moon's surface by August 21st, 2 crucial days before India's lander was scheduled to arrive. Russia would indeed win the initial, dramatic race against its rival. Luna 25 launched successfully from the Vostochny Cosmodrome on August 11, 2023, and entered the moon's orbit on August 16th. It managed to take striking photographs of the moon's surface, even imaging the Zond crater. All systems appeared to be functioning normally, and communications were good. Russian scientists then began the final, delicate preparations for the landing itself. The south pole of the moon is home to some treacherous, uneven terrain, and the scientists did not want a rough touchdown, which could potentially harm Luna 25 and its instruments. But then, the quiet went wrong. On August 19th, Luna 25 suddenly lost communications with Earth. No longer remotely guided, Luna 25 attempted to perform its own pre-planned orbital maneuver, which was meant to shift it from a circular orbit around the moon into the new elliptical path down towards the surface. However, a cascading failure occurred. The Bias-L navigation device, the one rushed into development by Russian scientists after the previous one failed quality control, sent faulty information to the ship's onboard control unit. As a catastrophic result, the thrusters fired for 127 seconds instead of the intended 84 seconds, violently pointing Luna 25 into a steeper and steeper descent. On August 20th, Luna 25 careened down towards the moon's surface at a pace far too fast to stop. Roscosmos scientists could do nothing but watch in horror as the lander hurtled into the terrain, accelerating faster and faster. Although no external cameras witnessed the final impact, it is easy to imagine the grim, silent result. The acceleration under gravity quickly turned Luna 25 back into its ominous namesake, a lunar coffin. Its lunar mission had not lasted a year, but only a few tragic days. NASA's Lunar Reconnaissance Orbiter later conducted a flyby, taking a distant image of the site of the craft's final resting place. Luna 25 had impacted incredibly hard, creating a crater about 10 meters in diameter. Russia had attempted to demonstrate to the world that it was still a great power in space exploration. However, the Luna 25 mission was utterly mired by external pressures and internal challenges. Western sanctions had, in an indirect but real way, sabotaged it. The rushed Russian replacement chip was not precise enough, or perhaps not hardy enough, to survive the high radiation environment of space. However, Russia's own choice to aggressively race its rival, India, had also created problems for itself. When I learned about its 2-day-ahead arrival date, it reminded me of a similar time when the Soviet Union's Luna 15 mission crashed into the moon only a few hundred miles away, and on the very same day that Apollo 11 landed. Luna 15 had been tasked with collecting moon rocks, just as the Apollo 11 astronauts were doing. Although it was unmanned, if America's mission had failed, it would have been a point of immense political pride for the Soviet Union that Luna 15 had managed to steal the American thunder. This was always about political point scoring. The Soviet Union didn't just want to get to the moon, it desperately wanted to get there first. And, inevitably, when you are racing to beat someone else, you take less time ensuring everything works as well as it truly needs to. And so, you run a significantly greater risk of tragic failure. Ultimately, just like with Luna 15, Russia's Luna 25 had the exact opposite effect that its country's leadership intended. Rather than demonstrating Russia's superiority in space exploration, it starkly illustrated the profound downsides of isolationism and rivalry over genuine collaboration. If Russia had still been working closely with trusted institutes like ESA and sharing in technological advances, perhaps it would be quietly celebrating a success right now. In many respects, it's a tragedy. Perhaps this can one day change. The future of mankind seems inexorably pointed towards the stars. If we are to thrive out there, it will be because we, as a world, choose to work together. The tragic fate of the Luna 25 mission can, and absolutely should, be a powerful learning experience, not just an embarrassing footnote in history, but this will only happen if the right lessons are drawn from it. Pride is not always a helpful thing. Rivalry can leave us dangerously isolated when we don't need to be, and can prevent us from thinking things through with the necessary patience. Although it is unlikely, it would certainly be a beautiful thing if our competitive efforts to prove our superiority to each other could finally be put to rest, perhaps buried forever in a frozen coffin on the lunar surface. Our gaze now shifts to Mars, the beautiful, mysterious red planet. Mars is absolutely littered with craters. Although Mars possesses a thin atmosphere, it is so tenuous that even small meteors manage to impact the surface before they completely burn up. The powerful high-rise camera on board NASA's Mars Reconnaissance Orbiter has been able to image many of these craters in exquisite, stunning detail, meaning we can examine impact zones on another planet like never before. Together, we will gently look at some of Mars's most interesting craters, and I will explain what you are truly seeing. We will start small. Here is a very small and incredibly fresh crater that likely formed sometime between 2006 and 2008. New craters have some very distinct, identifiable characteristics, specifically sharp, well-defined crater walls and clear evidence of fresh ejecta. Although this crater is just a few meters across, you can see the ejecta spread out over hundreds of meters. But this is over a flat surface. What happens if a meteor hits a slope? Well, that's exactly what happened here. The dust on Mars is extremely fine, meaning it can move quite easily. You can see the recent impact crater on this slope here, which caused a cascading avalanche of dust down the slope. The area around the avalanche looks soft and fuzzy because ejecta also spread out around the impact site. The dust is clearly precariously balanced, as even smaller, independent avalanches have been observed a little bit higher up the slope. So, if an impact caused this one avalanche, what caused the gentle movement you see in these long, impressive streaks? What you are looking at here is slope streak formation, one of the few active geological processes on Mars that we know of. We don't exactly know why these dark streaks are formed, But the leading theory is that due to the tiny size of Mars's dust particles, the smallest trigger, even just a slight gust of wind, can make the dust tumble and act like a fluid, similar to a snow avalanche here on Earth. The darker streaks are the youngest, the whiter streaks are older, the brightening caused by dust gradually settling back on them over time. It is quite a beautiful, dynamic sight. Let's move on to a particularly flat area of Mars. This area is quite boring and featureless. But zooming out a bit, we come across this big, kilometer-wide crater, which seems to have a distinct scar on one of its walls. This scar is actually caused by lava flowing down from the lowest point in the crater wall. The lava came from a nearby volcano that has repeatedly covered this entire area in molten rock from its eruptions. That's why the surrounding region is quite featureless. This used to be a vast lava plain back when Mars was far more geologically active. That makes this surrounding area here one of the youngest surfaces on Mars. I can only imagine what this area once looked like. The children's game, "The floor is lava," would have been quite apt. Let's have a look at another crater, heavily influenced by lava. This is Elysium Planitia, the second largest lava plain on Mars. 3D image of a crater in Elysium Planitia. This three-dimensional view, acquired from a stereo pair of images, clearly shows that the basin of this crater is remarkably flat. This is, again, due to lava flowing and completely filling the area from this vent found right in the center of the crater. This is an old, inactive vent now, meaning the surface hasn't been renewed for some time, evidenced by the many small craters dotted around the basin floor. There's another really curious crater I want to have a closer look at. This bizarre crater is found within the massive Schiaparelli crater, and it looks almost like a giant bullseye. We don't really know why it formed like this, although it could be due to there being different sedimentary layers in the bedrock that have been eroded smooth. Or it could be that this is actually a flat surface which just appears concave because the crater has been filled up by sedimentary deposits over time. If this is the case, the innermost layer would also be the youngest. We do not have a stereo view of that curious bullseye crater, so we can't definitively tell whether its strange appearance is due to erosion or sediment fill just yet. The quiet mysteries of Mars persist, waiting patiently for more data. But let's look at a crater that hasn't been completely filled in by one thing or another. This is the Peltier crater, a several-kilometer-wide feature that has also been rendered in beautiful three-dimensional detail. This crater is incredibly deep, stretching several hundred meters down from the rim to the basin. And along the inner wall, if you look closely, you will notice distinct features that look remarkably like old water channels flowing down the steep bank. While liquid water cannot exist stably on the surface of Mars today due to the extremely low pressure, scientists quietly theorize that water could still flow under the Martian surface. It is thought that slightly salty water, flowing out from the ground, could make its way down a steep slope like this for a short while, before the low pressure causes it to rapidly evaporate. In fact, on a different crater, this flowing process has actually been observed and documented. Notice the subtle differences in these streaks over the years time-lapse, showing changes in Martian gullies. Although we haven't confirmed that this entire process is solely due to liquid water, even though it remains the leading theory, it could still just be incredibly fine dust acting almost like a fluid, flowing down the steep slope. Now, let's shift our attention to a very old and incredibly deep crater. At first glance, You can clearly see inflow channels gently leading into the crater, and that the basin was once much deeper than it is today. It has since been partially filled or softened by the migration of dark sand dunes. Zooming in closer, we can clearly see the intricate sedimentary layers near the crater walls. Had this crater not been gracefully filled in by sand over deep time, perhaps it would have resembled the pristine, concave shape of the earlier Schiaparelli crater. There is a sense of ancient, enduring majesty about this crater. Its age somehow makes it look even more impressive, wearing the marks of time with silent dignity. For the very last crater we will explore today, we'll look at another magnificent 3D view. This unnamed, 15-kilometer-wide crater is found in the Demavend region. Seeing it from this oblique angle is truly a sight to behold. As we glide over the crater walls, you will notice that this crater has two tiers of walls and distinct peaks in the center. This structural complexity is due to the sheer size of the impact. Smaller, simpler craters tend to have smooth walls all the way down to a simple bowl-shaped basin. However, larger ones, like this, possess tiered walls with a significant uplift at the center. These are known as complex craters. Usually, such massive complex craters would be far too big to fit entirely within a single high-rise image. But this stunning view is a clever combination of several images stitched together, giving us an unprecedented look at such a large, intricately formed Martian crater. Coming closer to the crater walls, you'll notice those water channels appearing again, flowing down the side. You'll also note the remarkably smooth appearance of the terrain, which implies that fine dust has had a vast amount of time to settle here, softening the sharp edges of ancient trauma. So, there you have it, a quiet journey across some of the most fascinating impact scars on Mars. There are so many more craters I could have talked about, but sadly, they will have to wait for another time.